In previous segment, we had looked into different clusters of antennas, which are electrically small antenna, resonant antenna, broadband antenna, and aperture antenna. While the use of a single antenna completes the transceiver systems, sometimes certain applications may require additional radiation performances, such as increased overall gain, diversified reception, interference cancellation, radiation steering, which is the ability to maneuver the radiation pattern to a particular direction as shown in the figure above, direction of arrival estimation, and to maximize the signal to interference noise ratio, SINR. These enhanced performances can be achieved by adopting the array antenna system. In this session, we will look into array antennas. Let's delve into the details of an array antenna system. Motivation of having an array antenna as the front end of a wireless radio frequency communication system include to increase the electrical size of an antenna. Note that the antenna unit in the array is termed as element. To achieve higher gain and directivity, and to enable beam steering. This could be achieved by adopting the right array geometrical configuration, as the radiation flexibility is limited with the physical arrangement. For example, one-dimensional array is limited to only one-dimensional beam scanning. Optimum relative placement of the elements. Elements that are placed too near to each other will increase the mutual coupling level and limits the scanning range of the array, while elements that are separated too further apart will generate grating lobes that reduces the overall directivity of the array. Exciting the right phase amplitude and utilizing right antenna to generate the desired element pattern. These properties determine the performance and operational of an array antenna. In general, there are two types of arrays, namely broadside and end-fire arrays. In a broadside array, the dipole array are arranged linearly and in a vertical form. The total radiation pattern is perpendicular to the axis on which the array exists. Whereas, in an end-fire array, the dipole array are arranged linearly in a horizontal form. Radiation pattern of end-fire array is unidirectional, where a major lobe occurs at one of the ends. Another type of array arrangement is the one with parasitic elements. The element of both broadside and end-fire array, described above, consists of elements that are excited. However, in parasitic array, there are elements that are not excited throughout the operational of the array antenna. These units are known as parasitic elements. Parasitic elements do not possess an electrical connection between them to the driven element or to the feed. They are positioned so that they lie in the induction field of the driven element. Another influencing factor in an array design is the array geometry, which can come in the form of one-dimensional array, linear array, and two-dimensional arrays, square and circular arrays, as well as three-dimensional array, the faceted arrays. Before we go into the details, note that the total radiation pattern of an array antenna is heavily influenced by the radiation pattern of each element and the array factor, as shown here. Array factor is the summation of complex valued array weights in terms of amplitude and phase. Phase weights contain the properties of element position in terms of its spherical x, y, and z coordinates, while K is the wave number which contains the properties of wavelength. Now, let's look to the example given here. A linear array of 4 elements isotropic antenna arranged along y-axis. As this is a uniform isotropic array, the amplitude weight Wn is equal to 1. The summation of all 4 elements is as follows. We can write this equation with the first element positioned as 0 based on its position at y-axis and the last position of the element as total number of elements n minus 1. This equation can be written in a simplified summation form as shown here. In discrete mathematics, it was proven that the summation could be simplified as shown here. Hence, using this concept, the array factor of the 4-element array is equal to this equation. Playing around with mathematical factorization, the equation in the blue box can be rearranged and simplified as follows. Since the elements are isotropic antennas, the radiation of each element is equal to 1, and the maximum value of array factor occurs when phi, phase wave, are equals to 0. Hence, the total radiation pattern is equal to the array factor and can be written as follows. In cases of beam steering, phase shift is applied to the phase weight in order to generate radiation at the desired angle. In this session, we had looked into array antennas. Adopting array antennas in a wireless system enhanced the performances of the systems in the sense of increased overall gain and maximize the signal to interference noise ratio. While the advantages are achieved, array antennas in return increases the overall cost and complexity of the antenna systems. In the coming session, we will look into antenna measurement.